Human intelligence depends on the ability to link current observations with past experiences. Without that link, a powerful model functions as an amnesic pattern matcher, capable of processing a single prompt, but unable to reliably recall the steps it took 5 minutes ago. Bridging this gap requires a specific architecture of memory and state. Modern agent architectures split this recall into two distinct categories: episodic and semantic memory. Episodic memory acts like a chronological diary, storing specific, event-based experiences. For instance, logging that a user requested a sales deck yesterday, or recording the exact steps taken to resolve a support ticket. Semantic memory, by contrast, handles the generalized facts and preferences abstracted from those individual episodes. It doesn't just store the chat, it learns the pattern, noticing, for example, that a user consistently favors concise, bullet point summaries. In this framework, episodic memory provides the raw history of interactions, while semantic memory retains the practical lessons learned from that history. To manage this data, developers use two primary formats: vector and symbolic memory. Vector memory turns information into numeric embeddings, mapping them into a high-dimensional space. This allows an agent to retrieve information based on semantic similarity. If a query enters the system, the agent can find related concepts even if the exact keywords don't match. Symbolic memory uses discrete structures, like SQL tables or key-value pairs. While less flexible than vector search, these symbolic systems are necessary for enforcing exact business rules and logical constraints that a numeric embedding might blur. There is also the question of location. Internal memory is encoded directly into a model's weights during training, while external memory lives in outside databases. Because internal memory is static and expensive to update, current designs favor external architectures. These outside stores are auditable, can be updated instantly with new data, and allow for much stricter controls over user privacy and regulatory compliance. Ultimately, the quality of an agent's reasoning depends on how well these systems surface relevant information while suppressing irrelevant noise. While memory is a library of the past, an agent also needs a snapshot of the present. This is defined as state, the complete set of information at a specific time, including current goals and environment observations, that dictates how the agent behaves right now. Think of a game of chess. The rules of the game, how each piece is allowed to move, are stored in memory, but the current arrangement of the board at this exact moment, and knowing whose turn it is to play, defines the state. System architectures handle this differently. As Section 3.2 shows, stateless systems process every request independently, while stateful agents maintain a continuous thread of memory across multiple interactions. Stateless designs are easier to scale because the server doesn't have to track individual sessions. However, supporting a multi-step plan requires a stateful architecture that can persist task progress and user preferences over time. Explicitly formalizing these states allows designers to reason about transitions. This makes the agent's logic predictable and observable, which is essential for both safety and debugging. State is further divided by its lifespan. Session state holds transient data, like the recent messages in a single conversation, while persistent state covers long-lived information. Session data is typically discarded once a task is finished to keep the system fast. Persistent state, however, spans across devices and weeks of interaction, housing stable user profiles and historical summaries in durable databases. Managing these different timelines requires clear strategies for data governance. Without them, a system risks uncontrolled growth or amnesia that resets an agent's progress mid-task. Standard software relies on deterministic transitions, where an input leads to a predictable result every time. But LLM calls are non-deterministic. Factors like sampling and temperature mean the same prompt can produce different outputs, and consequently, different state updates. If a system relies solely on these unpredictable outputs, it risks a compounding chain of errors. To prevent an agent from drifting, designers wrap these stochastic LLM decisions in deterministic validators and guards to ensure the agent follows the intended logic. This logic is often managed through state machines. These frameworks model an agent as a set of discrete stages, such as planning, executing, or waiting, with explicit rules for how the agent moves between them. Combining deterministic workflow graphs with the flexible reasoning of an LLM creates agents that are both capable of complex problem solving and easy for humans to inspect and monitor. Reliable AI agents function by treating memory, context management, and reasoning as a single co-designed loop. This architecture allows the system to ground its stochastic decisions in a stable understanding of the world and its own history.